Okay, hello guys. So today we're gonna start a new topic is a parametric equation. Let me share my screen here. So the topic is parametric equations. So let me write here uh, parametric. Oh, sorry, I can type it better here. A parametric equation. So, so let's see what is the idea here. So here we're gonna kind of go back to integration. Uh, so we have learned from precalculus that a function that a graph like this is a graph of a curve, right? This curve can be the graph of a function if it passes the vertical test. Okay, so something like this, right? So this is a function, but something like this. Let's say something like this. This is not a function, right? Because if you use the vertical test, it has this value of x has different values of y, right? Here, 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 right? So this is not a function, right? Not a function. However, since the motivation of calculus was always or who created calculus, that was Newton. The idea of him was to solve real life problems, right? And in particular, he wanted to describe trajectories, right? So you have a canyon and you shoot something, it has this parabolic uh, design, right? So this is the trajectory of the missile. Okay, so we were thinking always on functions like trajectories, and that's the way you use it in physics. However, even the one over here is not a function, so you can see it in real life, right? Like if you have a sink, and you are that dishing, helping your family to wash dishes. You know that if you put a little particle in the water might follow some kind of trajectory like this, right? Uh, you have this is a piece of food, and it's gonna go like this and finally go into the sink. So even though this is not a function, you can see it in real life. So the idea is, how can we use calculus in these kind of graphs, diagrams that are not functions, but how can we study, right? Because if this is a particle, this particle has a speed, right? It's moving, so or has a velocity, right? And we know velocity. We associate the speed or velocity with the tangent line. excuse me, I was coughing. So so it looks like we still, if we can represent a real life problem, we can find, for example, in this case, the velocity of the particle, although we can find the tangent, the slope of the tangent line over here. Okay. So further, what is the distance? Let's say the particle started over here. What is the distance that the particle is running or until go to the center? So this is like an R-length integral. Okay, and another kind of trajectory could be something uh, weird, like something like this, right? So the particle is moving from here to here. So let's say you want to find the area of that part. Okay. So how can we use our knowledge of calculus to extend it to these graphs that they don't look as a function, but they indeed describe real life? Okay. So that's the purpose of these basically three last talks we have, these three last lectures, and then we were done by the semester. Okay. So that's what it's called. So all these curves that can be studied as functions, and we call it parametric curves. So this is a parametric curve. Uh, Even the functions are parametric curves. Okay. All these three are parametric curves. Okay. So the main relationship is the following, and you learn it in when you were talking about functions, right? So let's say this is our more familiar function, that is f of x equals x squared. Okay. So let me choose this point over here. What is, let's say this is 5. And over here, something happened. Let's say that point is 5, on the x coordinate is 5. What are the two coordinates of this point? So you guys tell me. If I choose this point, what is the coordinate of that point?
525.
525, correct. So in general, you have x, f of x. Okay. Now let's see a little bit more the next level of this. Let's take a circle. And then let's say this angle is 45 degrees, or let's say pi fourths, right? 45 degrees or pi fourths. Let's say this is pi fourths or 45 degrees. What is that? What are the coordinates of this point? If this is the circle.
Is it square root of 2 over 2 and square root of 2 over 2?
That's correct. That's not. That's correct, but I would like to give me the general one. Let's say instead of pi 4, I have the theta. So if this angle is theta, what will you tell me here? What are the coordinates? In other sense, what is the square root of 2 divided by 2 related to pi fourths? So if this is a circle, right? So we have x squared plus y squared equals 1. So this is very important. I mean, you guys should know, somebody should know. If you know that this is square root 2 over 2, square root 2 over 2, you know what I'm asking.
Is it 0.707?
No, I want you to give me the general, if you are in the unit circle, what is the other way to call these guys, this point? If you are in the unit circle. I make a review about it.
Oh, polar coordinates?
Yeah, what are those?
R theta.
No. Well, the objective is to get there, no, but before there. So this is cosine of and sine of.
Theta.
In this case, cosine of pi fourths and sine of pi fourth, right?
Yes.
This guy. And in general, this is cosine of theta, comma, sine of theta. So you see the circle over here uh, has like a different parametrization, because that's our first parametrization. We just never call it like that. This is my x and this is my y, and x and y depends of the angle theta. Okay, so long time ago, you know this, we haven't just explored about it, but another way to see this from calculus, from pre-calculus, was this. So x equals cosine of theta, y equals sine of theta. Okay, so and that's gonna be the kind of parametrization we are interested. Okay, so for in general terms, instead of theta, we could call it cosine of t, sine of t. Okay, so usually people use parametrization t. Theta is just for polar coordinates, but it's probably the most important one. So that's gonna be our objective. We wanna describe these graphs basically in terms of time. Okay, so we wanna say this guy is moving. This point is gonna be x of t, y of t. Okay. It's just the inspiration is sine and cosine, but also here this is x of t, y of t. Okay. And in this case, this could be just here you could forget about x. And since we are talking about parametrization, you just say t squared. So this f of t squared. And this point, any point over here is gonna be t comma t squared. You see? So it's like everything depends of only one parameter. That's what is called parametric. Okay. There is only one parameter, and it's basically time. In that sense, this projectile depends of the time. Over here, this is t squared to say. Well, probably minus. Yeah, some formula, right? Some minus t squared. It's moving to the right, so it's kind of a parabola. Let's put it. Let me put something more consistent, because otherwise, maybe this is maybe looks like something, right? Like t minus 1 squared. It looks like a parabola that it moves 1 to the center, and and uh, it's decreasing. It's going down, right? Something like that. So that's our objective. Okay, so so let's call let's say definition. Definition. Suppose that x and y are both given as functions of a third variable t. Suppose x and y are given as functions of a third variable t. Call a parameter. By the equations so it's our job to find these functions f of t and y equals, let's say, g of t. In the case of the circles, f was cosine, y was sine. Okay. By the equations, so we 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 call these equations parametric equations. Okay, so it's not that difficult. You have done this many times before. This is it's like we start doing like a little bit pre-calculus, then we will do some differentiation and then do some integration. So we're gonna do in three talks. We're gonna do kind of all this, but it's you see it's gonna be kind of easy. So example, uh, sketch, sketch, and identify the curve defined by the parametric equations x equals t squared minus 2t and y equals t plus 1. Okay, so what do you have to do? You have to do like your first, like what you were doing in college algebra. Okay, so you have to make a table. This is t, this is x, this is y. So you choose some values. You can choose -2, -1. 0, 1, 2, and then you plug in and graph it over here, and then you try to sketch the graph. Okay, so let me give you 5 minutes to try to sketch the graph by hand. Okay, so plug in this point, plot this point, evaluate these points, and then plug it in the graph. Okay, so let's find the values. So the first one is -2. So, and you need to plug in over here. Well, let me do the first one somewhere. So let's do it. No, let me do it here. X of -2 is, I do -2 squared is 4. -2 times -2 is +4, right? So I get 8. Yes or no? That's what you guys were doing?
Yes.
Yes, okay. So why is y of -2? What do you
Negative
get?
1.
-1. So -1. So what is x of -1?
3.
3. What is y of -1?
0.
0.
So what is x of 0?
0.
0.
Y of 0?
1.
X of 1?
Negative 1.
And x of y of 1?
2.
Then x of 2?
0.
0.
And y of 2?
3.
3. Okay. So with those, we can graph now. So now, to graph, you forgot about the t. And only get these two guys. X and y. Like you used to do in your pre-calculus. So that will be x of a is -1. So 1, 2, 3, 4, 5, 6, 7, 8. And let's say -1 is here. So this is my first one. This guy doesn't like. Okay, let me put it there. Well, no, it's not right. My pen doesn't let me make. Let's just put it there. Okay. Then x of 3 is 1, 2, 3. X of 3 is 0. So it's over here. The next one is x0 is 1. So x0 so is 1. So it's over here. Right? The next one, x of -1 is 2. So put -1 over here. So 1. This is 2. Is over here. So far, it looks something like this. Right? Now, the next one is x of 0 is 3. So let's go here. So over here. So if you keep graphing, you'll find symmetry. It will look something like that. Okay. So that's my graph. But then you have extra information because you could say this guy is t. You could forget about the x and y's. And you could say this is t equals -2. You can say this t equals -1, right? This one is t equals 0. And then this is t equals 1. And this guy is t equals 2. And so on. So you see, that's what is interesting parameterization. Of course, t in this case, time, it doesn't make too much sense to have -2 seconds, -1 second. I guess it could be like before you started the experiment, right? So you start the experiment at time equals 0. So I guess this could be an interpretation. But you see how easy is to figure out, and this is going to be really important in calculus 3 especially. Okay, so let me give you a definition. Oh no, let me give you another example. So graph now, example, same problem, same question. What curve is represented by the given parametric equations? So please graph the following. X equals cosine of t, y equals sine of t, but this time t is between 0 and 2 pi. So maybe, so I'll let you try to guess, okay? So try to plug in at least four or 5 points. 6 points, let's try to find 6 points. I'll let you try that, so I'll give you 5 minutes. Okay, so what do you guys get? How does it look like? What do you think that is?
Like a wave.
Yeah, it's a wave, but it's a very familiar wave. So this is X and this is Y, right? So so let me, since it's cosine and sine, so I need to use values that I know, right? So 0, pi fourths, pi halves, uh, pi, 3 pi halves. Yeah, maybe just go for pi, 3 pi halves, all those. Well, I guess it's okay. 3 pi halves, then 2 pi. Okay. So when it's 0, what is cosine of 0?
1,
1. And sine of 0?
0,
0. Cosine of pi fourths? What is cosine of pi fourths? Square root 2 over 2, remember? Somebody said. And sine of pi fourths, square root 2 over 2. That's the only intersection. Well, that's the first intersection. Well, the second intersection. No, the first intersection they have cosine and sine from 0. Then cosine of pi halves. What is cosine of pi halves?
0,
0. Sine of pi halves?
1,
1. Then um, then cosine of pi
-1,
and sine of pi?
0,
0. And then 3 pi,
0,
3 pi halves. Cosine is 0 and sine?
-1,
-1. And then cos
1,
2 pi 1 and sine of 2 pi
0.
0. Okay. So you guys want to do another guess? What is this? What is this? Yeah, okay. See, yeah, I see what you guys are saying. There is a wave. But let's see how it looks, okay? Because you have first, we need to grab the x and y's, okay? So when x is 1, y is 0, right? So x1, y0. So this is 1. The next one is x square root 2 divided by 2, y square root 2 divided by 2. So that's something probably here. And let's say this is 1. So it's something here. So it's something over here. This thing is hard time. Let's see. All right, I don't know. It's a big one. I don't know what's happening here. Let me mark it like that. Yeah. So over here. Okay. The next one is pi halves, but I cannot forget about the pi halves, and it's when x is 0, y is 1. So over here, right? So basically over here and over here. Those are the 3 points I have grabbed. The next one is when x is minus 1, when x is minus 1, y is 0. So I'm going over here. So you guys want to make another guess? What is this going to be?
It's a circle.
It's a circle. So when x is 0, y is negative 1. Okay. And when x is 1, y is 0. So basically, I went this way. But now this is important. This is a circle, but the particle is moving against the clock. Okay. So my particle is moving in this direction. Okay. That's something very important. So your parametrization not only describes the path of the curve, the path of the particle, it describes the direction where it is going. Okay, so this is very interesting. So and then so we're gonna define like more general. So definition or yeah, definition. Let's say definition. The definition is initial point and terminal point. Definition. The curve with parametric equations x equals f of t and y equals g of t and t is between a and b, right? Has initial point FAGA and terminal point f of b, g of b. Okay. So over here, we started at the point, we can call it, let's see where it started from 0 to p, 2 pi. So this is my A, this is my B. So my starting point is cosine of 0, sine of 0, and my let's call it initial point. And then my terminal point. Let me change of color. So, well, okay. Terminal point is a cosine of pi, sine of pi. So that's why you started at this point. So what do you guys say? What is cosine of 0? Cosine of 0 is 1. Sine of 0 is
0.
0. Oh, sorry, no. And this is cosine 2 pi. Cosine of 2 pi is
1.
1. And sine of 2 pi is
0.
0. So that's why you started where you finish where you started. Okay. So you start here, and then you end at the same point. This is usually called a closed curve. Okay. Okay, so before I show you more graphs, like how messy they can be, how beautiful. You know, for the people that like Nintendo, PlayStation, all those. So this is a lot of programming is based on this kind of parametrization, right? So, for example, you parameterize things. So I remember uh, when I used to have programming classes at my university, they make us make rectangles, right? And we were able to move the rectangle over here, like displacements. So you could also make a happy face and then transform it into a sad face. Probably you guys have done similar stuff in programming. But you know, what you do is, so these points are the same, right? These points are the same. On time, they don't change. These 2 points are the same, but these points are changing on time. So you start making a displacement. So this is a graph. This is a graph, and then you will change it to this graph. Okay, or no graph, a curve. Okay, so so with parametrization, you can do that kind of interesting stuff. But you know, that was long time ago. So computers were very basic. Well, at least the ones that I could buy, right? My computer was really basic. Other people have really good computers. I didn't. Uh, but I remember in high school we have some really these kind of computers, but you had to. The Windows didn't even exist, I think, when I was in high school. So you had to really program just to write anything. You had to program, and so what Windows did, Bill Gates became rich because he make it easy. He make it accessible, just like Word. You know, Word, uh, like before it was like using C++ or MATLAB. That was that kind of programming you had to do for anything. To see you to do anything, you had to be to make a table. You had to use kind of programming. So it was a pain. But now it's so convenient that you think it's easy. But what is behind of all this, at least in this imaging on this graphing, is all this parametrization. So you cannot overlook on mathematics because every people got rich with mathematics, right? Uh, so hardly they give back. But without mathematics, there is nothing. And they wouldn't be rich as they are. Uh, so yeah, so many options. For example, I remember there was this competition. I don't know if you have seen Silo like this, I think, or with Y. I don't remember. But this is to buy houses. So there is a lot of data there because they basically have any house in the market and any house in any part of the United States at least. And you go to the map and they will tell you the price of that house. And they have so much data, they have to change how the pictures, the pricing. So just to manage that data, it requires some programming challenge, and they have awards, famous problems for programming. Okay, so yeah, so this is cool. You could think this is the beginning of programming. This kind of stuff we are doing, if you wish. Okay, so let's see. Try to answer the same question. What curve is represented by the given parametric equations. So we're gonna say x equals sine 2t, y equals cosine 2t, and y and t, sorry, between 0 and 2p. Let me give you 5 minutes to do this one. And so make the table and tell me what is different. Why is this parameterization is different to the one before? They look almost the same. Okay, guys. So what do you think? What is happening? What is different this parametrization to the other one? So first question, is the same curve or is a different curve? Another question. Somebody's working on it? So let's do it. So we do T, X, and Y. So we do the same. We have an idea. We know exactly what it is because we just graph it, right? So it's cosine sine 2t, y cosine 2t. It should look very similar or basically the same, but for some reason I have a 2 over here and I have a 2 over here. So let's see. So I'm going to do 0, pi, and no, probably I have to do more. I'm gonna do I'm gonna do more. I'm gonna do pi fourths. I'm gonna do pi halves. I'm gonna do pi. Okay, to start. So when when t is 0, what is sine of 2t? Is sine of 0, right? So what is sine of 0?
0.
0. Oh, let me see if I put it right or put it wrong. Oh yeah, it's good. Yeah. So it's 0, right? And then y is cosine of 2 times 0 is 0. Cosine of 0 is
1.
1. So well, when I get x and y, right? I'm doing at x is 0, y is 1. So I'm over here. So you see, my beginning, just my beginning is different, right? My beginning in the other place was different. So what is sine of 2 pi fourths? So you do it, sine of 2 pi fourths, right? It's sine of pi halves, and what is that? Sine of pi halves is
1.
1. So this is 1. And what is cosine of 2 pi fourths?
0.
It's cosine of pi halves, that is 0. So this case, x is 1, y is 0. X1, y0. Anyway, and now the next one. Sine of 2 pi halves. So is that sine of pi? So sine of pi is
0.
0. Thank you. Yes, 0. And then cosine of pi halves is
Negative 1.
sorry, yeah. Cosine of 2 times pi halves is cosine of pi, so it's negative 1. So now in here, I'm going to 0, negative 1. So I'm going here. So basically, since these are sines and cosines, so I mean, you might have a doubt, but if you have a doubt, this is a circle. So try this. You can try over here pi eighths. So cosine, no, sine of 2 times pi eighths, it gives you sine of pi fourths. How we know that is? square root of 2 over 2, right? And then cosine will be the same. So that one is this one over here. So this is a circle going in this, but this time is moving in this direction. In the direction is clockwise. Sorry, oh, this circle is not nice circle. Sorry, let me make a good circle. Ah, better, right? And then cosine of pi, let me see. And the next one is cosine 0, 1 minus 1. Cosine of 2 pi is 0. Sorry. Sine of 2 pi. Sine of 2 pi. So if you're still lost with your cosines and sines, let me teach you a trick. I already teach you this, but let me teach you again. So this is my sine, and my cosine goes like this. So then I fill the graph. This is 0, this is pi halves, this is pi, this is 3 pi halves, and then this is 2 pi. Same thing here. This is 0, this is pi halves, this is pi, this is 3 pi halves, and then this is 2 pi. Okay. So I asking for cosine sine of 2 pi, that's this is sine. This is sine of x. Well, let's put it sine of t. Call it sine of t, cosine of t. So and cosine of 2 pi is 1. So over here I go x0, 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 y1. So that's, I finish over here. So this one over here, sorry. It goes back to the initial point, you see? So I went from 0 to pi, I already got a circle, right? But in this direction. Okay. Now, what is another difference? Somebody notice another difference? This one is clockwise, the other one was not clockwise. So what other difference do you notice? Did I finish or not yet?
Not yet.
Not yet. Because look at my range is from 0 to pi. So these two make my particle go faster. So I still had to go another round. So I'll go one turn. So I'll get 2 turns. Okay. So this parametrization, and if you are an electrical engineer, you already know this is frequencies. You know this one goes faster. Okay. So I don't know, not any person that took trigonometry knows that when this guy is bigger than 1, well, the particle is moving faster, right? The one thing is normal. Yeah, one thing is, oops. One thing is this normal sign, and something different is when just in halfway you do one sign and then you do 2 signs. Okay, so that's what happens when you have sine of 2t. Okay, this is just sine of t. This one is sine of 2t. That's why you run twice the circle. Okay, so let me show you. Let me know. Oh no, if somebody's asking me questions, let me see. Okay, people was answering in the chat. Okay, so let me show you some nice graphs. This is on the notes. It's also, let me show you in the notes. Let's see. Oh, no, I don't have them in my notes here. I have it in the other computer. Let's see. Yeah, no, I haven't loaded here. But what I can show you is the book. In the book, you will see, and by the way, this is the last chapter of the book. So in our book, so the only bad thing of this book is sometimes has mistakes in the examples. But and also it says 829 pages, but it's just because it's very spread out. I think they could do a better job doing that because it looks scary. But we're basically here: parametric equations and polar coordinates. And you see what I was talking about. Like this is I was saying that it's a sink, but look at this. This is a parameterization. This is a totally parameterization in nature. Okay. So all these are examples, more examples. You can go ahead and check it out and try to solve this by yourself. And then you'll see the different graphs they can create, right? But what I want to show you, so these more examples. I'm going to show you sort these guys. You see these guys? This is the kind of stuff that you can do with parametric equation. It's kind of beautiful symmetries. It's basically just repetitions because you just keep going. You do one, and then you keep going. So you are doing kind of the same curve several times, and that's how this symmetry shows. In the notes, you have more examples. And then he shows the relation between the circle and the trigonometric equations again. You probably remember that. So this part. But I want to show you. No, these are derivatives. We're going to do that next class. I don't want to do that today. I think we already did. I don't want to give you too much. When I start a new topic, I don't want to give too much stuff. But I want to show you, I want to show you those figures. I will show you in the notes more figures, okay? I was looking for more figures. In the notes, we have a lot of figures. So you will see our figures. But you see, we're doing now the length of a curve. We will find the length, okay, of this parameterization. And then we just use a formula. And then you're finding the R length of this, okay? And then we can also find surface area, but I don't think we're gonna do surface area. I think it's enough with length and area. We're gonna do area. So the other section I wanna show polar coordinates. And we're gonna do that next class. And then you can start looking at this. So please review this. This is your pre-calculus class. So how do you change to polar coordinates? You remember when they give you in polar coordinates, you have to change to trigonometric to rectangular coordinates. So you're supposed to, well, I mean, I taught that in pre-calculus. I'm sure you saw it in your high school. But it's good to review. So that's by sure I'm gonna ask you one problem of that. And then that could be an easy 5 points. Okay. So we give you the point in the polar coordinate. So these are polar coordinates. So it's like you are changing dimension. In polar coordinates, you're moving on circles and radius, like a spider. Okay, so you are becoming Spider-Man here, but you're a spider in the net. That's how you move. Okay, that's okay. So it's like another geometry, and then we can graph interesting things. And probably here you can see the kind of graphs I'm talking about. So we can do really fancy stuff with, for example, we can do this one, you see, and it's just this kind of graph. This is radius, a plus b theta on the theta is the angle, where theta is the angle. This is spiral. It's a spiral, right? You can do this cardioid. You can do this other one. You can do the rows. And look at the parametrization. A cosine b theta, a sine b theta. But this is on polar coordinates. We do that probably on Friday. This will be for Friday. But look at this one. This is 3 sine pi theta. Okay. So if you are romantic, so just send this to your boyfriend or your girlfriend. And you can do it on Wolfram Alpha, for example. And you see, this is the model, the representation of the spiral. Okay, guys. So I think with that we can stop today. And just kind of give you an idea of what we're gonna do. So this topic is easier. It's easier than series. It should be definitely, don't scare you. Try to understand it well, because that definitely is gonna help you in the final. Because I had to put at least one problem of this. Okay. So so please take a look at the book, and that's section 7.3. And let's see, section 7.4. Yeah, we'll do area and arc length. And this is just basically this equation that we know. But in polar coordinates, it's gonna look like this. And that's it. So you just try to have to the integral in terms of theta. And then we're done. So for example, you have to find the area, okay, of these rows. And it's amazingly easy. Okay. So that's all that that's gonna be the end of the story by Friday. So I think by Friday we will be doing all this. But I want to show you the end of the book. And the conic sections, we're not gonna do conic sections. You already saw this on pre-calculus. Not sure why they have it here. Maybe for optics. They usually do. But I did this in pre-calculus when I taught pre-calculus. But I just want to show you that we're really close to the end, right here. And over here. Over here. 5. And the Q concepts and appendix. We're done. Okay. So we have 3 more sections to finish. So don't get discouraged. What is coming is easier. So what we're gonna do is easier, but you need to, you need to see the lectures, to do your homework. It's gonna be easy homework, not that much homework, but that will be this could be the easy problem from the exam, from the final. Okay, guys. So I'll let you go. I will open the new homework. So you guys don't have questions. I'll let you go.
Thank you, sir.
Okay. Bye. Okay, bye.
Have a good day, sir.
Bye. Thank you. You too. Well, Lorena.
Sir, I have a question.
Yes.
Exam 3 is on Thursday at 7 p.m., right?
Yes. This exam is optional. So if you are happy with your 2 grades, you don't have to take it. But if you want to improve it, you will take it.
Okay. And is it the same format as exam 2?
No. This one will be half and half.
Okay.
Two or three problems multiple choice and 3 problems or 4 problems to submit.
Okay. And we only pick like 4 or 5 out of the 6 or
I
7?
don't. I haven't written. The
Oh, okay. All right. Thank you, sir.
Oh, probably I guess gonna make it short, but you have to solve everything. I will probably make it just short. The 5 problems.
Okay. Thank you,
Like
sir.
sample exam. Look at the sample exam.
I got a question real quick about it, about his question. What if we take the third one since it's optional and we do bad on it?
Well, then you don't unload anything.
Oh, okay.
You
I
just
just
tell
wanted
me,
to,
yeah, I prefer not to submit. You
yeah,
don't submit.
I just wanted to make sure on that one. Thank
Yeah,
you,
sure,
sir.
no problem. Yeah.
Have a nice day.
Okay, bye, man. Okay, guys, so I'm finishing the meeting.